Right, so in this unit, I'm going to go through 2.5 programming languages and integrated development environments. I'm just going to do it with clicking because it's easier to swap programs. So it's not a very big unit, so I'll whip through it reasonably quickly. So what you've got here is you've got the characteristics and purpose of different levels of programming languages. So you've got low level and high level. There are more generations than this, but they get quite sort of wishy-washy, talking about sort of fifth generations like AI kind of making it stuff for itself, stuff that doesn't really sort of properly exist. Even fourth generation is kind of a loose term. So really think of it as first, second, and third. Fourth is sort of thrown in there. So where are we? Right. So the first level language, the lowest level. This is the lower it goes, the more to computing language it is. So this is actually the only language that the computer understands. This is machine code. Okay, it is literally written in essence binary, but the way people often type it in is to type it in hexadecimal, but it is just binary because you should know how to convert hexadecimal to binary. So that's 1/8, that's 24, the first bit, so that's 24. So this is, it's typed in hexadecimal here, but you've got to understand that machine code in essence, so ignore that really, ignore the bit about hexadecimal, just understand that really it's just binary. So in case you didn't understand this, on the CPU, every instruction is a number. So add might be 158. So then you would put 158 and then, whatever the next bit would be, probably a memory address. So obviously, it's difficult to understand, very hard to write in, very hard to find errors. And yeah, there you go. So the second one, what someone did was they thought, well, rather than let's type these numbers in, why don't we give each number a word? So that's what mnemonics are. So basically, so down here, load, that might be like 139. So instead of having to put 139, you can write load. It's easier to program in than machine code because at least you can see some words. But you got to understand that it will take loads and loads and loads of commands to do anything really simple because it's a lot of doing stuff. So it's considered a one-to-one relationship with machine code. So what that means is there is one mnemonic for each number. So this in Python, when you write like print, it does like 100 commands to do that. But here, literally, when you say load, it is one number. It's just like it's just instead of writing numbers, you write a word. So it still needs to be translated, turned into machine code, because obviously computers can only execute machine code, and that's done in what's called an assembler, where it assembles it. It's actually not very difficult to write an assembler because basically it's a one-to-one relationship. So basically you've got a big table and load is 110, and you just convert load to that digit, that binary number, and then you just go through converting everything to binary in from a table. Like, this is what it means, this is what you convert it to. The only time I've ever seen anyone use it is for device drivers because they need to be super quick. Because obviously the thing with this is you only write what you need and you can really be optimized, so you don't have extra stuff that Python or other languages would put in because they bloat everything a bit. But obviously it's still ridiculously difficult to write in. So that's second generation. Okay, but that's still low level. So remember, the low level is machine code assembly. The high level languages, let's go with the real one, third gen. So the third generation one, like Java, Basic, C Sharp, C++, and the many more. Python, of course, I should have put in really, seeing as we learn Python. Much easier to understand, program, easier to find errors. They use English keywords. But like it says here, one instruction translates into many machine code. So this if args less than 1 message equal, this 3 lines here might be like this entire page. So just understand that translates to quite a lot of stuff. So yeah, I mean, that's the benefit of it. That's a lot easier to understand, a lot easier to find errors, and easier to teach people how to use it. So third generation is the way to go. Fourth generation languages, they're known as declarative languages. Basically, the idea behind them is that you don't code anything. You sort of ask questions and it returns the answer. So you haven't got to worry about how it does things. You just got to ask it a question and it gives you an answer. SQL is sort of an example of this, but a lot of people would say that's quite wishy-washy. AI is kind of what people talk about. Like you would say, like I won't say the name of it because I'm in a room with one of it in, but Amazon's voice-activated Alexa device. You could argue in some ways is possibly some sort of fourth gen because you ask it to do something and it just does it. You don't actually know how. But obviously, as all these things are, you're very limited by what you can ask. So, I think it's a bit wishy-washy, really. So that's 4th gen. I wouldn't worry about it too much. They won't ask about that. They'll ask about 3rd. They'll ask about one of these in the mock and in the real exam. They very rarely ask that. I mean, so much so in the real worksheets they give you, they don't even have 4th gen on the activity sheets. It's gone. It's in their PowerPoint, but it's not on the activity sheet. So, right. So that's that bit covered. Okay. Now we're going to go on to the purpose of translators and further bits. So basically, a translator is used to translate something from one language to another. So as you can see here, you've got 1st gen, 2nd gen, 3rd gen. So obviously it needs to be translated into machine code. So that is what a language translator does. It changes it from one language into machine code eventually. Right? It doesn't go dun, dun, dun. It just goes dun or dun. In assembly, you use an assembler to make it into machine code. But in a 3rd generation, you use a compiler or interpreter. So assembly uses an assembler, and a high level language uses a compiler or an interpreter, which we're going to look at now because, we have to look at the two things. So as I said here a minute ago, that 3rd generation programming languages such as these need to be translated into machine code. And that can be done in two ways, using a compiler or an interpreter. A compiler looks through the program, compiles the program completely, and then executes it. Now, the benefit of this is that it optimizes the code because it looks through the whole thing at once. It's used at the end of development because once you've compiled it, it's done. It's done its compilation at the end. So you do it when you're finished. Error reports created along with the error code. So as you compile all the code, it will look for any errors it finds before it even runs it, rather than running it and then finding an error later on. Obviously, there are some types of errors that can only be found at runtime, but sort of other errors that can be picked up before it runs, it will find. One other thing is that the source code is safer. So what I mean by this is, I don't know why they didn't put that in their list. This is their list. Is when you write code, so I'm going to show you in a minute, here's some code for a very boring hello world in C#. If I compile that, then they can't see what the code was very easily. There are some tools they can use to sort of try and extrapolate it back, but they don't work perfectly. They don't work really well at all. But in theory, the source code is a lot safer because it's now into binary. It's literally in numbers now, not in those words. And it will just be in the machine code, maybe, I don't know, 6K or something that would be, or whatever it was, and that'll be it. In an interpreter, what it does is it translates line by line. Okay? The benefits of that are that it's quite quick to run. Not when it's running, and this is the bit that's really tricky to get over to people. What I mean is, so let's say, and this is pointless, but if I want to compile this, I have to build it. Okay? So it builds it. There you go. It builds it. That took about 1 second, granted. But if you build, say, like Chromium, which is one of the bases for Chrome, it takes like 4 minutes, 3 minutes to compile the whole thing because it's a massive program. And that's 3 minutes every time before, if you make a change, you've got to compile it, you've got to test it. So it can take a long while to build the executable, the binary, before you run it. But when it's running, it's fully optimized because now the computer doesn't need to do any translating because it did that translating before. Compare that to an interpreter that translates and executes code one line at a time. It is essentially translating it and then running it, translating it and then running it. So yes, when you press go at the start of the to run the program, it's going to run straight away. But it won't run as fast when running because there'll be periods where the processor is wasting time translating the next line, which will already have been done for it here. So that's quite good when there's lots of development going on, because if you're completely changing your code all the time, then that's a lot quicker because you're going to have to run the code thousands of times. And at the end, you can always compile it into a final binary. So it's not like you can't combine them. You can interpret and then swap to compile. But anyway. So, right, last but not least, and quite an easy one, the IDE. An integrated development environment is used to help you write a program. It is a program itself that assists you in writing a program. It's a whole environment. Okay, the most well-known one is the one that I keep showing you, is Visual Studio. And this is, I've zoomed in quite a lot, by the way. This is not normally how it is. Normally it's much further out. But essentially you can see here, look. So auto-completion. So watch as I start typing. Console. Now I've got a list of all the things. And this is really useful because sometimes you know that it's console dot, and then you're like, oh, background color. Well, I didn't know you could change the background color of something. And look, I actually haven't used C# to change the background color, but I'm probably going to guess that it's equal hash. Probably like that. I'm going to guess. I'm making a wild guess that you put the color. You might give a color. It has given me an error. Cannot convert type string to system.console color. Right, okay, so there'll be a system.console color. So there you go. So I had no idea how to change the color of the background text, because it's not something I'd ever use. Because when I do use C#, I don't use it in the console. And then dot, and then I've got the color as well. So I didn't have a clue what that was, but the error actually told me how to fix it. So let's do .red, and then when I run this, let's have a look. Wow, look at that red background text. Brilliant. That's such a great thing. So I guessed. So you can see that. Look how good that was. And that was a great example because I genuinely don't ever use the console because I write games and we don't write. There's no console in that's not how you do it. So I thought it was that. So I did that, hovered over it, and you can clearly see. Look, cannot implicitly convert strings. So I've typed a string, but it expects system.console color. So you can see how useful that was. That just solved my problem. Brilliant, and it's made a great example to you guys. So you can also see that it highlights colors and other things when you select. A bracket, you can't see it. It's not very dark, but it does go grey, telling you which bracket is similar. You can even do things like hide blocks of data. You can also set a breakpoint, which is really good. I think it's here. There we go. So you set a breakpoint, and then if you run it in debug mode, what will happen is it will run to that point and stop. So now it has not run that piece of code yet. If I could just get those side by side, right? So then what I can do is I can go, right, I'm going to step over that, which will do it. Step into, it doesn't really matter which one I press. Step into will go inside it and look at the subcode, but it doesn't really matter because there isn't any subcode with this one. But anyway, the point is, if I press F11, now I'm stepping through, look, and I'm running it line by line. Obviously, that's the end of the program. But what I'm saying is I can run it line by line and check things. I can also set up these watchers. So if I've got any variables like age equals, obviously I've got to do int age equals 12. I can set a watcher up on that. And then on this window, it'll show me what age is. And whenever age changes, I can see it change. So you can see that that's a really useful tool. And that's basically how IDEs work, really. That's their version. So breakpoints are really good. You can see what I just did there. Error reporting, auto completion, like I showed you a second ago, brackets matching, and it highlights any errors. Like you saw that. It was a great example. So yeah, have a look at the questions and you can then try those out.